Hi everyone. Today I want to talk about the reaction stoichiometry lab. In this lab, what we're going to do is determine the stoichiometric coefficient of a reaction where we don't really know exactly the identity of the species in the reactants, meaning that we don't know the exact chemical formulas. So an example would be like this. Let's say you're given A plus B and we know it forms C. What would be the coefficient of A, B, and C in this case if we don't really know the formulas of A, B, and C? Now, this is different than other reactions that you've seen because usually you know the actual formulas of these molecules, so it's easy to balance out the atoms. But if you don't know the actual formulas, you can still do the coefficients, but now you have to do it experimentally. So let's first talk about the actual reaction that we would be working on. This is called a complex ion formation reaction. And a complex ion, at this point, you just need to know that it's an ion that's formed by a transition metal cation combining with something called a ligand, which is a species that donates electrons to the transition metal ion. So in this particular case, an example of a complex ion is zinc with 4 ammonia surrounding it. The zinc is the transition metal, the ammonia is the ligand. The feature, though, that I want you to focus on about complex ion is that they all are very colorful. The color is actually going to be a useful property that we would use later on to determine the concentration of these complex ions. So now let's talk about how we're going to determine the coefficient of a reaction where we don't really know the formulas of the reactants and the products. Well, we're going to use a method called continuous variation to do this. And the idea of a continuous variation method is the following. I'm going to mix A and B in such a way that the total stays exactly the same number every time I mix them. So in this case, I'm saying that I want the number of moles of A and number of moles of B to always add up to 4 moles in every mixture where I have A and B together. So it could be 1 and 3, 2 and 2, 3 and 1, right? All of those would always add up to 4 moles, okay? And at the same time, I'm going to try to figure out how much product I'm going to get from every one of those mixture. And you'll see very shortly that we can determine the actual coefficients of A and B just by looking at how much product we're getting. Okay? Now let me explain this table a little bit. To be able to show you that this method works, I have to start with something that actually has coefficients in it. So in this case, I'm going to use that same reaction, AB goes to C, but in this case, I'm going to say that my coefficient for A is 2, for B is 1, and for C is 1. Okay? And again, I want to make sure that in every experiment I do, the number of moles of A plus the number of moles of B equals 4 moles. So as you can see, here I'm running various experiments where I'm mixing A and B. You can see that for every mixture, the total adds up to 4. 0.5 plus 3.5, 1 plus 3, and so on. Now, as I said earlier, for every one of these mixture, I'm trying to calculate how much product I'm going to get. You can do this through stoichiometry, right? The first thing you have to do is you have to figure out what is the limiting reactant in this particular experiment, and then afterwards use the limiting reactant to calculate how much product you're going to get using the stoichiometric coefficient. Well, I've done this for you. So the limiting reactant for the first 5 experiments is A. You can do that fairly easily by taking the number of moles of each of these reactants, dividing it by the coefficient. And then for the last 2 experiments, the limiting reactant happens to be B. And there's an interesting point right here. For this particular mixture, both reactants are actually used up. So there's no limiting or excess reactant. Both reactants are completely gone. That's what we call a stoichiometric quantity of reactants. Okay, so now let's calculate how much product we're going to get. Again, you can just do this fairly easily using stoichiometry. You'll find that for each of these experiments, the number of moles of product starts to increase as I increase the amount of A, and at some point it starts to decrease. But what's really interesting is if you look at the pattern of these numbers, this number here where you get the most amount of product also happens to be the same as when there's no limiting reactant, when both reactants A and B are stoichiometrically related. That turns out to be the point that we're looking for, because if you look at the number of moles of A and B here, 2.66 to 1.34, we can reduce this to whole numbers, and that ends up being 2 to 1. Why is 2 to 1 so important? because 2 to 1 also happens to be the coefficients for A and B. So what I just showed you is that we have a method now to determine the coefficients of a reaction when we don't really know the formulas. The only thing we need to do is just mix A and B in such a way that the total is always constant and look for the point when we generate the most amount of product. At that point, the ratio of the two reactants would be exactly equal to their stoichiometric coefficient ratio. Now let me point out one more thing here. You notice that as I'm going increasing the number of moles of A, I go by values of 0.5. So it goes from 0.5 to 1, 1 to 1.5, 1.5 to 2, and so on. Now, you might ask yourself at this point, how is it that I know that when I go to 2.5, instead of jumping directly to 3, I actually go exactly to 2.66? And that's a fair question. I would not know. In a real experiment, most likely what I would do is go to 2.5 and then go to 3 and to 3.5. In other words, I would miss completely this point right here, which is actually the point that we're looking for. So then you say, well, does that mean the method doesn't really work? Well, it turns out that it still does, because instead of just looking at the raw data, you can actually plot the data. When you plot the data, then you're actually able to find out exactly where that highest point for product is going to be. Let me show you how. Okay, so here's that data again that we had earlier. So let's imagine now that I actually do this in a real experiment and I miss that particular point, which is the point where we actually have that stoichiometric relationship. So I go directly from 2.5 to 3 without stopping there at the 2.66. What's going to happen? Well, I can still find out that my stoichiometric ratio occurs at 2.66 by doing the following. I would plot on the y-axis the number of moles of product I have, and I would plot on the x-axis the number of moles of one of the reactants. It could be A or B, doesn't really matter. This plot is useful because of the following. Let's say I plot that first. You can see that the numbers keep going up right here, and then eventually it reaches 1.25, and then the number starts to go down, right? So I can plot these first 5 data points on the green dots right here. So that's the first 5 data points. And then the last 2 data points I plot here using the red dots. And then what I can do is, of course, I can fit the plot with a straight line on both sides. Now notice what's interesting here. The intersection point for those 2 lines happen to be higher than either of the plots. So it's actually right here. And that tells me that that's the point when I have the most product. But isn't that exactly what we're looking for? We're looking for the point where we make the most product. So if I go from here and look at the x-axis, now I can find out how much A I need to make the most amount of product. Now, how do I find out the B? Easy. Remember that the A and the B adds up to the same number every time. So if I know the A, I can also find out the B by subtracting the number of A from the total. So that's how we're going to determine the maximum amount of product and the stoichiometric ratio of A and B using this data. Even though we can't get to that exact amount in the data itself, we can still get it from the plot.